For this second part of the morning, Yulong Lu from the University of Massachusetts Amherst, which will talk about statistical sampling with birth-death dynamics. Please, Yulong.
Thank you very much. So thanks. First, I want to thank the organizers for inviting me to speak in this nice workshop. And thanks everyone for coming to this talk. So I will be talking about recent work with Jianfeng Lu, Jim Nolan, Diane Slipchef, and Lihan Wang about statistical sampling with the birth-death dynamics. So this is based on two works. One is with Jianfeng and Jim, and this is the main focus of this talk. And the other is ongoing work with Diane Slipchef and Lihan Wang. So the second part, Lihan will talk about in more detail in the next talk. I'll focus on the earlier work with Jianfeng and Jim. Okay. So if anyone has any questions, please feel free to ask. Okay. Okay, so here's an outline of this talk. So I will give a brief introduction of sampling problems and also a review of a few typical sampling methods. And then I'll focus on the PDE perspective for constructing sampling schemes. Then I'll move to the idea of accelerating sampling using the birth-death dynamics, and finish with several conclusions, and then give a few future directions. So what is a sampling problem? So suppose we are given a target probability measure pi defined on the d-dimensional Euclidean space. With a Lebesgue measure, Lebesgue density of this following form. It's proportional to e to the minus v, with the normalization constant is given by z. We typically assume that the constant z is unknown because it's too expensive to compute, in particular when d is large, or the density function is too complex. Okay. So the goal is to construct a sequence of random samples, xi's, such that either xi's are RID distributed according to pi, or in some other cases where you are only interested in empirical measure of the samples, you want to make sure that the empirical measure is close to the target measure. Okay. So why are we interested in a sampling problem? Well, sampling allows us to compute any statistics of the target distribution. Because a lot of large numbers tells us that you can approximate the expected value of any observable function against pi by the empirical average of the observable evaluated at the samples. Or in other words, you can approximate the pi by the empirical average of the sample. And also the CLT tells us the error you make in this approximation typically decreases as you increase the number of samples. With the rate is one given by 1/2, and in particular, this rate doesn't depend on the dimension of the distribution. So this means that the Monte Carlo sampling can actually overcome the curse of dimensionality when you use the Monte Carlo average to approximate the exact average. So that's why we focus on sampling, why sampling problem is important in many problems. So a typical way or traditional way to construct sampling schemes is to use a Markov chain Monte Carlo. The basic idea is to build a algorithmic Markov chain that's denoted by xt. T can be discrete or continuous, such that the invariant distribution of the Markov chain is given by the target distribution pi. Okay. And one of the major goal of the study of MCMC is to kind of construct a Markov chain so that the distribution of the process is convergent to the invariant distribution as fast as possible, as t goes to infinity. Okay. There has been many works on this topic on constructing sampling methods, non-trivial Monte Carlo based on non-trivial diffusion, either overdumped or underdumped schemes, Hamiltonian Monte Carlo, or metropolized version of either one of these. PDMP processes for constructing samplings like zigzag, bouncy particle samplers, and also recently standard variational green descent, and many others. So I think that the previous workshop in this semester program was mainly focused on different kinds of sampling schemes. So I will not, repeat those methods, but I will focus on somehow the underlying mathematics behind those methods. This is the PD kind of description of essentially most of the methods. So that's what I want to talk about, the PD perspective for sampling. And later I will somehow show that you can actually tune somehow the PD basically about the gradient flow structure of the PDEs that underlie these dynamics. Later I will talk about the different ideas for constructing the metric and also the gradient flows, so that you can get different convergence results for the scheme, for the PDEs and also for the sampling scheme. So maybe I'll first recap the perhaps the most canonical choice or canonical dynamics for sampling is called Langevin dynamics. Here I'm writing down the overdone version of that. It's given by this stochastic differential equation. And in practice, people usually use the discretization of this continuous time process, and so that you can get discrete updates of this the samples. Of course, those discretized version will usually introduce some bias in the invariant measure, and one way to correct the bias is to add a metropolis step on top of this analog scheme to correct the invariant measure. So what I want to say about the PD is about the density evolution of this equation. So as we know that the density evolution equation of this xt is given by the so-called Fokker-Planck equation. It's a linear elliptic, linear parabolic PD. And there have been many ways to show that the convergence of the PD or the convergence dynamics by using for example, functional inequalities or the coupling arguments from probability to show the exponential convergence. So I want to address the gradient flow structure of the Fokker-Planck equation, because as I said later on, we're going to choose different metric, and or in some other cases you can choose also the objective functional to get a different dynamics with a different convergence rate. So the first result goes back to the famous JKO paper in 1998, which says that the Fokker-Planck equation is a gradient flow of the relative entropy with respect to the two Weissenstein distance. Okay. And this actually gives many ways to actually study the convergence of the Fokker-Planck equation to the equilibrium. For example, the lambda displacement convexity of the energy functional, the relative entropy, with a positive lambda will imply the so-called log Sobolev inequality, and this will in the end leads to that the convergence of the density function to equilibrium is exponential with the same rate. Rate is given by the displacement convexity constant or this log Sobolev constant. Okay. So this picture, this gradient flow idea, actually is very powerful because it gives a way to view the sampling from different perspective. This suggests that the sampling can be viewed as a minimization problem on the space of probability measures. Okay. So this idea goes back to this point out by this paper by Soner and also by Ma and et al. So this motivates a lot of questions like how do you actually design a loss function on the space of measures, so that the loss function attains the equilibrium attains a minimizer at the target distribution. and how to actually construct the metric for the gradient flow, so that your dynamics is converging to the invariant measure as fast as possible. Okay. So and I will talk about a recent dynamics we find using burst test idea, which somehow has a different gradient flow structure from this JQ paper, or this Wasserstein gradient flow. And I will show that this new dynamics actually has very surprising good convergence property under certain minor conditions. Okay. But before that, I want to address there's one important issue about this long-event diffusion and also many other dynamics. It's the slow mixing time or slow mixing rate. For sampling multimodal distributions, the mixing time of long-event diffusion can be very long, exponentially long, due to the so-called matter stability, which means that your dynamics can spend a very long time around the each several modes of the distribution, or in other words, the local minimum of the potential function in the exponent, and then suddenly jumped between these local minimums. Okay, so for example, for the target measure given by the eta minus v divided by epsilon, with a v given by a double well potential, the log subfield constant the lambda scales like e to the negative c divided by epsilon with a positive c. So when epsilon is small, this lambda is very tiny. Okay? So the rate you get for long-event dynamics is very, very small. So then the major question is, can we actually construct other efficient dynamics for overcoming the multimodality issue with an intrinsically better mixing time or mixing rate than the long-event diffusion? Okay, so I have to define what I mean by better. It will be clear in a second. And basically, I want to say that can you get a rate which somehow doesn't depend on the barrier of your potential? Okay? So that's a goal. So let's see. So now I'm going to move to the burst test dynamics, and I will first introduce these dynamics using this picture, and then we'll go to the convergence property of this dynamics. So so what's the idea behind this burst test dynamics? So let's first think about how do we actually sample multimodal distribution. Okay, so I want to think about this problem from a continuum level, or from the PDE level. I want to think about how do we evolve the density function to the target distribution from a given initial condition. Okay, so let's say my target distribution is a double well distribution. Sorry, is a distribution with two modes, which corresponds to the double well potential. So this is drawn. This is indicated by this red curve. Okay, it's pi, and then I will start my distribution with a single well potential. So that's my rho 0, which has somehow the support around the first mode, or the mode on the left. And let's think about how we're going to move this rho 0 towards pi. Okay. So what long-event diffusion does is that there are two terms in the PDE, right? The first term is the diffusion, the Laplacian term, which somehow smooths out this density. Okay, so you smooth out the rho 0 to some rho t, right? T is bigger than 0, which means that you somehow move the profile a little bit higher, right? As you rounds t bigger and bigger, and also at the same time you have a drift term, or the transport parts, which somehow drive your density, drive your the profile to the high density region, right? So on the right side, you want to move your particle somehow a bit higher to this mode on the right. Okay, so but if you think about you want to somehow move the rho 0 to pi in a cheaper way, or in an optimal way, this may not be the optimal choice or the best choice. I mean, because you can somehow do the following, right? So that on the left, you see that your rho 0 initial density is much higher than this target density, right? So the mass is much bigger than this pi on the left. So what you can do is you can actually drag down a little bit of the initial density towards pi, right? On the left hand side. On the right hand side, you see that the initial density is much lower than the pi, the target density. So the mass is tiny on the right. So you should think about how to increase the mass on the right directly. Okay. So at the points where the current density is much higher than the target, you should decrease the rho 0, the density at that point. And conversely, if at a point where the density is much less than the target measure, you should increase the mass at that point. So you know, this is what we call the burst test. Bursts want to kind of increase the density at certain points, and that's that means that I want to decrease the density at certain points where the current density is much higher than the pi. So that's a very simple idea. And how do I actually construct such dynamics for doing this? Well, it's actually very simple. We can do this by using ODE, although it's going to be an infinite dimensional ODE because we want to evolve the particles at any evolve the density at any location. So let's consider this following ODE. dt rho is equal to minus alpha t times rho t, where the alpha t is basically the difference of the log of my density and the log of the pi, subtract by the average of the same difference against my current density. Okay, so why this is doing what I just said? This is doing the burst test mechanism, because if you are at a location X where the rho t is much higher than the pi, so that the difference of these log densities is going to be much larger than the average. So the alpha t is going to be positive at that point. Then, you know, by this OD, if alpha is positive, this dynamics tells me that I should decrease the function value of rho t at that point. Okay. And on the other hand, if I'm at location X where rho t is much less than pi, so that this, you know, the log densities is difference of log densities is less than the average, then alpha is going to be negative. So then this coefficient will be positive. So this dynamics will increase the mass, okay, at X. So this is a simple dynamics which somehow adjusts the mass of rho t according to the relative ratio or relative difference of rho t and pi. So I want to mention a few facts about this dynamics. The first, you can recognize from this form of this alpha that, by the way, the alpha is usually called the burst test rate because this adjusts how much you or the speed of the evolution of rho t, right, at any given point X. Okay. So alpha t is the burst test rate. And as you can see from this definition of alpha, that alpha will be 0 when rho t is equal to pi. Okay, so this means that you know, when rho t is equal to pi, this dynamics will not move. This means that pi is a stationary distribution of this equation. And as I said, rho t is much larger than pi, then this guy will decrease, and rho t is much less than pi, this rho t will increase. And also this is the ODE, and it's a nonlinear, non-local ODE. Nonlinearity coming from this the log term of rho t, and non-local term because of this average of the log difference against the current density. So it's not the independent ODEs, right, at different locations, but those guys have rho tx actually talk to each other by this average. So the integral term also guarantees that the mass of the rho t is preserved along the evolution. Okay, if you take the average, the integral of rho t, you look at the evolution of that, this will be static. Okay. This also is somehow the necessary condition for a sampling scheme, because you want to say that in the end you are actually get a probability measure, right? If you start with a probability measure, you end up with a probability measure. Also, this dynamics is independent of the unknown normalization constant of the pi. This is very important because, as I said, in practice, it's hard to track the normalization constant. And the reason why this is the case in this first test equation is because you see that if you multiply the pi by any constant, the log pi appears twice in this equation. So they have different signs in front of log pi. So if you multiply the pi with some constant, these two constants will cancel. So in fact, this alpha doesn't depend on the normalization constant of pi. So there's one important feature of this dynamics, which to me is actually a bad feature, but later I will kind of want to get rid of this bad issue, which is the support of rho t does not expand in this dynamics. This is because this equation is given by ODE. If rho is 0, let's say is 0 at certain point, right, or the x is within certain sets A, the rho 0 is 0, then the ODE tells me that my rho t will stay 0 for any positive t in that set. Okay, so from this equation, the support of rho t doesn't expand. Okay, so this is bad for us because in the end we want to do sampling, right? So if your target measure or the measure you want to sample from has a full set, full support on the whole space, but if you start with your density with a compact supported initial condition, right, then you will never end up with a target measure because your t will stay compact supported, and the support will not expand. Okay. So this is bad news for us from this first test. But on the other hand, if you get rid of this, right, that's compact support, meaning that if you initialize a density on the whole space, then you can actually end up with a good regime, which I will talk next. So this is basically what I want to say. First, about the local convergence. So assume that rho t is the solution of the Bose equation with the initial condition of 0, and we assume the initial condition has a bounded relative entropy against pi, and also the rho 0 has a full support. Okay, the rho 0 is always positive for all x. Then you can show that the rho t is also positive for all x and all t. Moreover, you can actually show a pointwise convergence. Okay, for any given x, this rho t, the solution of the equation actually converges to pi, and also in the pointwise sense, and also in the sense of KL divergence. Okay, this follows from the fact that the KL itself is a Lyapunov function of the Bose dynamics. Okay. So this is about local convergence, which says that if you initialize a density, which has a full support, then you end up with a convergence. Okay. So what's really surprising about this dynamics is not about the convergence; it's about the convergence rate. Okay, which I'll state as a local convergence rate. I will state the results, and I will give a comments on this why we call it local convergence, and later on, in fact, we improve this result and get a global convergence as well. Okay. So let me state the theorem. So assume that rho t is solve this Bose equation with initial condition at t0. Okay, let's say assume that rho t0, the KL divergence between rho t0 and pi is less or equal to 1. Okay, so this is somehow a good initial condition in the sense that the rho t0 is not far from pi. Right? It's bounded by 1. And we also assume that the rho t0 has a lower bound compared to the target measure, meaning that the infimum of the ratio between rho t0 and pi is strictly bounded from below by a small constant. The constant is defined by e to the minus m. Right? The m can be very large, so this lower bound can be very small. Okay. So what do we get for the convergence? Well, you can show that for any delta, which is a small constant, the KL between the rho t and pi contracts exponentially after some time t star, okay, with the rate given by 2 minus the 3 delta. So think about this is a constant, where the constant is actually close to 2. Okay. From t bigger than t star, and what is a t star? T star is the t0, the initial time, plus the log of the m divided by delta q. So forget about delta. Delta is some like arbitrary constant. You can ignore that. It's a fixed constant. The really interesting thing is about the dependence on m, or the lower bound in this ratio. So think about m can be very large. Right? M is let's say 100 or 1,000. So the lower bound is actually tiny, which somehow allows us to initialize the density in a larger class. Then the delay time, or the waiting time for us to get the exponential convergence is only logarithmic in m. Okay? So the delay time is actually not horribly long because of the log dependence in this m. And also this rate you get for the convergence is a constant. Right? It doesn't depend on the barrier. It doesn't depend on the potential function. It only depends on it's a universal constant. In this case, it's 2. Okay, so this is what I mean by local convergence. What I mean by local is that I have to assume my initial condition is within a small neighborhood of my pi. Okay, the initial condition is in a small neighborhood of pi, in the sense that KL is less than 1. Okay, and also I will assume this quantitative lower bound or quantitative lower bound on this density ratio. Okay. So this is very nice. This is a nice result, because you can actually get a universal rate compared to Langevin in the case where the target density is a double well. The rate is exponentially small, but in this case, the rate is the same. It's universal. It doesn't depend on the potential or the target measure. Okay. So as I said, this is the results we proved in this first paper with Jianfeng and Jim. And recently we actually improved this result by removing this initial condition, this KL is less than 1, or this warm start condition. We only need this lower bound assumption on the initial condition. This is in the ongoing work with Diane and Li Han. And Li Han will talk about this result in the next talk. Okay, so that's about the convergence property of the burst dynamics. Are there any questions about these two results? Okay, so now I'm going to talk about the effect of the burst test in accelerating the Langevin dynamics. So as you see from the statement of results, we have to assume that the initial density has a lower bound, right, compared to the target density. In particular, this rho t has a full support on the whole space. How do we actually get a lower bound in practice? How do we make sure that the density is actually bounded from below? Or in other words, how do we actually search the modes? Right? It's essentially saying that you have to initialize the density which cover the full modes, right, or any place on the whole space. Right? So the short answer is you can use diffusion process, because even if you start with a complex body distribution, if you run the Langevin diffusion or any diffusion process for a positive amount of time, then you know that the density is going to be always positive, right? Although it may be tiny, but it's always positive. Okay, so that's a one way to get the lower bound assumption in this burst test dynamics. Of course, you can use other things, but or focus on Langevin diffusion, because combine Langevin with burst test, later on we'll have a very nice structure on the PDE side. So another question is, how large is a T star? Right? As I said, T star is actually depends on T0 and also the log of M. I want to get the estimate for the delay time in many situations. Okay, so let's think about a simple case. Okay, I'll try to answer this two questions in a simple example, and then after that I'll give some numerical examples as well. So let's consider a simple case where my target measure is supported on the one-dimensional torus from -1 to 1, and V is 1 divided by epsilon of the cosine squared pi x. Okay? If you plot the graph of this pi, you will see there are actually two modes, which correspond to the two global minimum of this V. And I will only initialize the density, okay, initialize the dynamics from one mode, or the density which is 2 pi times the cutoff function on the left mode. Okay, so my residual has a compact support. Okay, and let's think about how do we move this compact support density with the diffusion, and then let's say run the diffusion from certain time, and then let the burst test take over for the rest, see what's going on, what can we get for the convergence. Okay. And in this case, we know that mixing time for Langevin dynamics is very long, it's exponentially long, because of this small log scale constant on this density. The mixing time can be improved to log 1 of epsilon. If we do the following, so if we run the Langevin dynamics for a certain amount of time, let's say we run the Langevin from 0 to 1, okay, and then we run the burst test dynamics from 1 to the rest, to infinity. Okay, so let's see why we can improve this this mixing time to log 1 of epsilon. It's because if you first solve this Langevin equation, or move this part, the profile according to Langevin diffusion, which means you solve the Fock-Planck equation, then at time 1, you can get some kind of lower bound for the density. Okay, this can be proved in many ways. You can get a tiny lower bound. It's exponentially small in epsilon. Okay, the lower bound. But after that, once you have this kind of lower bound, then the burst test dynamics tells me that after the T star, which is somehow constant plus log of this M, the exponent, in this case 1 over epsilon squared, then you basically get exponential convergence. Right? E to the minus there should be a 2 something, 2 over here. So this KL contracts exponential fast with a constant rate after this waiting time. Okay, so basically means that you can actually, if you want to make sure that the KL between the T and pi is less than epsilon, let's say, then you can just less than delta, let's say, then you can wait for this amount of time, and then after that you only take a log of delta time to reach to delta, right? To make sure that the KL is less than delta. Okay. So compared to this exponential long time, this log 1 of epsilon is much small, right? The mixing rate is much better than this standard Langevin diffusion. Okay, so so this is what I said. I want to somehow use the Langevin process to get a lower bound, or to get the full support of the dynamics, and then we'll run the burst test dynamics to get a convergence. So this suggests I can combine this two mechanism, Langevin diffusion and the burst test, and then you can actually do a simple combination of these two equations to write down a new PDE. We call it bus as Langevin, accelerated Langevin dynamics. And this is somehow the fourth-column equation corresponding to this dynamics. And it turns out this equation has a very nice structure in the sense that this is also gradient flow of the KL divergence with respect to a new metric. It's called the Wasserstein-Fischer-Rho metric. The distance is defined in the following way in terms of the kind of the dynamical formulation, where this blue parts correspond to the Wasserstein gradient flow, Wasserstein distance, where this red part corresponds to the Fischer-Rho distance. This Wasserstein-Fischer-Rho distance was first proposed in this three papers on the second line. And also this new distance was also used, or this new gradient flow was also used in the training process, training dynamics for neural networks. Okay, in this last reference. Okay, so that's about the gradient flow structure. So this is the equation we just talked about. This equation is not convenient for us in practice because the Langevin part has a nice particle interpretation, meaning that you can view the rho t as a density function of a stochastic process. But if you add the burst test part, and because of a nonlinear burst test rate, this will no longer have a particle interpretation. Okay, so how do we actually implement this guy in practice to get a sampling scheme? Well, we can do the following. So the first step, we're going to smooth out this equation with a kernel, meaning that when update or change this burst test rate with a kernelized rate. What I mean by this is that the initial alpha is defined by the difference of log densities, subtract the average. So now I'm going to write this guy. I can write the difference of log density as a log of the density ratio. Then the non-local PD corresponds to the case where you modify this ratio by a convolution. You convolve this density ratio with a kernel. Of course, when kernel is close to Dirac, then this dynamics is going to be close to this original PD. But the reason we will modify this equation by this kernel is because this new PD can be actually implemented in practice. In particular, you can actually show that this solution of this PD can be approximated by the empirical measure of a new burst test interaction particle systems as n goes to infinity. What is the new interaction particle system? Well, this consists of two steps. Step one is that you run the Langevin dynamics for each particle, okay, independently. And then you run this to a certain time, a random time. Okay, so each time it will somehow carries exponential clock, and when the clock runs up, then you should swap you should either kill or duplicate the particles according to the following rate. Okay, and the rate is defined by this empirical version of this lambda x rho t. On the particle level, is approximated by this number. Okay. So if you iterate these two steps for a small time step, and you let time step go to 0, and in the end, and also that n goes to infinity, then you can actually show that the rho t is close to. So this dynamics, the empirical measure of the dynamics, is convergent to the solution of the non-local PD. So I want to show you one simple simulation result, so you can see the acceleration effect of this burst test dynamics over the Langevin diffusion. So what you see on this movie is that on the top left is you see the 8 modes. Okay, so it's actually a Gaussian mixture on the 2-dimensional space. And I initialize the particles on or near the top mode. Okay. On the top right, you see the vanilla non-divine diffusion process of the ALA scheme, and on the top on the bottom left, you see the SVGD dynamics. We see deterministic particle scheme for sampling distribution, and on the right, on the bottom right, you see the burst as accelerated non-divine dynamics. Okay. So let's run this dynamics. You see that this last movie, you see that initially the particles are around the top mode, but then after a few steps, some particles identify more modes because they are more particles are duplicated on the bottom. So once they identify all the modes, then they start mixing very fast around the modes. Okay, so that we get a good approximation. The empirical model get a better approximation to the target density. Okay. While the other samplers, for example, ALA, only a few particles have moved to the bottom, and SVG is deterministic, so there's no randomness. You see that the particles actually going in a deterministic way, so it's very rigid. And again, very few particles identify to the bottom modes. Okay, so let's go back. Okay, so let's summarize. I discussed a continuous time burst test dynamics, which can achieve an asymptotic convergence rate, which is independent of potential barrier. As I said, I stated as a local convergence without, and Li Han next will talk about the global convergence, which actually show that this is a global convergence rate. It's not just the asymptotic convergence rate. And in this dynamics, in the convergence results, we do not assume any function inequalities like Poincaré or log Sobolev on the target distribution. This was usually assumed in non-divine diffusion or other diffusion-based sampling schemes. In this case, we do not need this function inequality to get convergence, but we do need that the initial condition has a full support. Okay, so that you can basically mean that you have identified all the modes, and we care about the mixing time once you identify all the modes. Okay. So and also the burst test dynamics can be actually implemented using an interactive particle system. There are a few open questions on this dynamics. The first one is a quantitative error analysis of this burst test dynamics, which consists of two questions. One is a long-term convergence of the kernelized dynamics. So far, I've been talking about localized dynamics, where the equation is local. But if you have a non-local term, the kernelized dynamics, it's still known how to actually prove the convergence of that. And also how to show the mean field estimates, or quantitative mean field estimates of the burst test interacting particle system to the kernelized dynamics. And then finally, I think the big question in this gradient flow idea is that how to actually tune the Wasserstein metric to actually get the optimal rate, or to get the best rate you can get. In our case, we get this burst test dynamics. Somehow this allows us to get a uniform rate without dependence on the potential barrier. But is any other dynamics which can do this and can potentially remove the lower bound assumption in the density? That's still open question. So I think I have to stop. Thanks a lot for the attention.
Thank you, Yulong. So we have time for one question.